तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we shall continue our discussion on TTL gates. We were discussing the LS TTL gate and some variations of it. What we saw the last class was the open collector, okay, which is used mainly so that you can wire the output of two gates. Okay, you have the wired AND connection, which you cannot do otherwise in a normal TTL gate with active pull-up, because in such a connection, okay, you may have cases where the output is not defined, okay, as well as you may have the problem of very large currents flowing. Okay. So, you can only do it with an open collector gate, okay, and the advantage you derive is because of the wired connection, okay, you save a lot of gates. Okay, you can obtain more complex logic functions using fewer gates, but at the same time you have to pay for it in terms of speed. Okay, it is not going to be as fast as the normal TTL gates. Okay, so today's class we shall look at just one more variation. Okay, so I'll just draw the LS TTL gate once again. This is the LS TTL NAND gate. So, by now I think you must be quite familiar with the circuit, and you should be able to draw it very easily. Okay, so right, sorry, there is some resistance here. Then you have the input diodes. Okay. Now the resistance values, just note down. So this was 20K, this was 8 kilo ohm, this is 1.5K, this was 3K, and this was 120 ohms. Okay. All right. Now, so this is the LS TTL gate. Now, the variation I was talking of last class was the tri-state logic. Okay, that is, normally in a logic circuit you expect the output to be either logic 1 or logic 0. Okay, that is, either the output is high or the output is low. Okay. Now, you may have a third option, okay, where the output is neither high or low, but it is called the high impedance state. For example, when do you require it? If you are connecting a number of gates, all right, say a number of NAND gates to a common line, okay, a common bus, say, all right. So these may be the outputs of some circuits, okay, connected to a common line, and at any particular instant you would like the output of this gate, for example, to be available on the line, and the other should not affect it. Okay. For some other instant you may want this the output of this gate to be available on the line. Okay. So what should happen, so when you enable this gate, okay, all other gates should be disabled. Disabled means they should not have any effect. So as if it is an open circuit. Okay. There is an open circuit here, all right, then only it is as if only one gate is connected to this line, all right. So, this is possible only when this output is in the high impedance state, okay. That is, there is no, that output is neither sourcing any current nor sinking any current, okay. So, as if it is open circuit, all right. So, that is possible in this configuration here if you can switch off both this transistor, the pull down transistor, and also the upper half. Of course, I am sorry I missed out some this you have complete circuit, you have 2 more diodes here anyway, okay. So, when you switch off this lower half this pull down transistor as well as the pull up, okay. So, in that situation it is as if this is floating, okay. There is no neither it is going to source current nor it is going to sink current. So, how do you do that? It is a very simple alteration, okay, or a simple addition, additional components are required, okay. What you do is you have another input here, diode here, okay, just like this one, all right, and there is another diode coming from this point here, all right. It joins up with this input here, okay. All right, okay. So, you have 2 diodes here which is connected to this common point, okay. One is connected at this point here and the other is connected at this point, all right, okay. Now, what happens is when this input goes low, all right. So, this diode is conducting, okay. It is going to pull this voltage down here low. So, what is going to happen is these 2 transistors are going to turn off, okay. At the same time, when this point is low, you see that this point also is going to be low enough, so that these transistors cannot conduct, okay. So, basically what is happening is when this input goes low here, all right, all the transistors, okay, all the transistors here are going to switch off, okay. It is just, see, this diode acts as just like another input here, okay, to this gate, all right. So, at this point because of this diode. So, when any input is low, you know, these 2 transistors are off, okay, and by this additional connection here, okay, this point is also made to go low. If this is 0.2 volts, this is going to be around say 0.5 volts or so, okay, because of the drop of the Schottky diode, okay. And if you have 0.5 volts here, there is no way that these transistors can turn on, okay. So, it ensures that all these transistors are off and as well as these are off. Now, when this point goes high, okay, when the voltage at this point goes high, what happens, okay. These none of these 2 diodes are going to conduct, okay. Now, like in a NAND gate, you know, this is like a NAND gate. When any input is high, the output is governed by the other inputs, okay. It has basically no effect on the gate in a NAND gate, all right. So, when this goes high, then the output is going to be governed by these 2 inputs, okay. That is basically in a NAND gate, when any input goes low, then only the output goes high, okay. So, if all the input goes high, then the output is going to be low, all right. So, when you make this high, okay, this diode does not conduct, okay. So, it does not have any effect. Also, this diode does not conduct, okay, all right. So, this also does not have any effect. So, basically when this input is high, okay, it behaves as a normal 2 input NAND gate, okay, and when this input goes low, it goes to the third state, that is the high impedance state, okay, and the output is going to be floating, all right. So, this is another variation, okay. So, you are also this type of gates are also available in the TTL series, okay. So, this is basically these are used as buffers, okay, where you can either connect or disconnect, okay, the output of a particular circuit onto a common line. Okay. So, this I just wanted to tell you as a small variation of the normal TTL gates. Okay. All right. Okay. Now, continuing our discussion on the advances in the TTL family, okay, the next series of TTL gates came out in the 80s and was called the advanced series. Okay. You have the advanced Schottky, okay, as well as the advanced low power Schottky. Okay. Okay. Now, the advanced Schottky is basically the circuit is similar to the Schottky gate, or I should say it is very much similar to the circuit of the 74LS. Okay, this is 74LS 00. So, the advanced Schottky 74AS00, okay, is very much similar to the 74LS00 circuit, except for the fact that since it is supposed to be a high speed gate, the resistance values are quite low. It is similar to the Schottky series. Okay. The circuit itself is quite similar to this. Okay. There is no variations in circuit, except that the resistance values are the same as the 74S00. But all these advanced Schottky gates, okay, they have there is a lot of improvement in technology. Okay. For example, all these advanced Schottky LS series, they are fabricated using 3 micron technology. So, you see that it has come down from 6 micron to 3 micron, okay, as well as other improvements, like instead of junction isolation which you had in the previous gates, you have oxide isolation. Okay, that is, the individual transistors, okay, which were isolated using p-n junctions. Okay, I have drawn the previous transistors configuration. You had seen that there are p-n junctions which are used to isolate the individual transistors. Instead of that, you use a more improved technology where you have oxide, you know, silicon dioxide, okay, which is used to isolate the individual transistors, and this reduces the parasitic capacitances to a large extent, okay, and improves the speed. All right. So, these are some of the improvements in technology, okay, which took place in the intermediate time, and these were incorporated in the advanced series. Okay. So, 74AS, okay, the improvements were quite remarkable, that the delay was 1.5 nanoseconds, whereas the whereas the power dissipation for this gate was 20 milliwatts. Okay. So, the delay has come down to 1.5 nanoseconds from 3 nanoseconds in the Schottky 74S00. Okay, and the power dissipation of course remains the same. Okay. All right. So, you see that there is a lot of improvement. In fact, the advanced Schottky series is the fastest of all the TTL series available. Okay. So, this is the minimum delay which is reported. Okay. Then you have the advanced low power Schottky, which is again a variation of the 74LS. Okay. But here some modifications of the circuit has taken place. All right. I will just draw this, okay, circuit. Okay. You will observe that in the 74ALS, okay, this part of the circuit remains the same. Okay. Whatever modifications are on this side. Okay. So, let me draw it. The inputs you will see is slightly different. Okay. So, you have PNP transistors at the input. I will explain the reason for that. So, here you have PNP transistors, then you have some more one additional transistor, as you can see here. And then you have the normal structures on this side, as I said. Okay. Here you have some diodes. Going to the input. Okay. Then the resistance values, I shall just note them, write them down. 40 kilo ohms, 60 kilo ohms, 15 kilo ohms. 3 kilo ohm and 6 kilo ohms. Okay. So this is the circuit of the 74 ALS00. As you can see that this part of the circuit okay, is the same, okay, except for the fact that of course as you see here that the resistance values have been even increased even more, okay, that is to achieve even lower power dissipation. Okay, when you compared with the 74 LS00, in the 74 ALS00, okay, the resistance values have been increased, but this part of the circuit remains the same. What has been done is an additional transistor has been introduced here. Okay, all right. Now this additional transistor, the purpose of introducing an additional transistor is to have some additional gain, current gain. Okay, so normally you see that when this transistor turns on, basically you have to turn on this transistor. Okay, so if you have an additional transistor, this entire combination of transistors will now have, if you put one more transistor, you have an additional current gain. Okay, so this transistor is going to switch on faster. All right. So an additional transistor has been introduced here for that purpose. Okay, but if you introduce an additional transistor here, what is going to happen to the input output characteristics? The input output characteristics is going to get shifted by another say 0.6 to 0.7 volts, isn't it? Because the input voltage, in order to turn this on, the input voltage has to be more by 0.6 to 0.7 volts, because here you require at this point now you require 3 transistor drops, 3 diode drops, okay, to turn on this transistor now. Okay, so you require the input output characteristics is going to shift to the right, okay, by around 0.6 to 0.7 volts. In order to but you see all these TTL families are made compatible to one another. Okay, they are all upward compatible. That is, you know, if you have a circuit made of the earlier TTL gates, okay, if you replace it with a later version, just take out the older chip and put a new one with a later version, it should work. It should not create any problems. Okay, so the compatibility must be maintained. So how do you ensure compatibility? Okay, to do that, they had introduced a PNP transistor here. Now this PNP transistor is in the emitter follower configuration basically. Okay, so whatever voltage you apply here, so this is the emitter point of this PNP transistor. All right. So instead of the diode, you have a PNP transistor, and this PNP has a drop, VBE drop here, okay, in this direction. All right, the base emitter drop in this direction. So this compensates for the additional VBE drop because of this NPN transistor. All right. So in order to compensate for this VBE drop of the NPN transistor, another PNP transistor has been introduced, which is in the emitter follower configuration. Okay. So that is the purpose of the PNP transistor. You also have some diodes, you see here, additional diodes. This is for you see that this input, this point here, that is the base of this transistor, is connected to the two inputs, so that when any input goes low, okay, this transistor will be switched off. This transistor must be switched off fast. Okay. So when this input goes low, it has direct connection to this point. Okay. So this base charge can be switched, can be removed, okay, and this transistor can be switched off. The voltage here is going to fall instead very fast. Okay. So that is why you have diode connections from this point to both the inputs. Okay. So these are so this part, okay, basically again to summarize, you have an additional transistor here that the purpose is to increase the internal current gain. Okay, so that the output pull down transistor can turn on faster. Okay, but to compensate for this additional VBE drop here, because the characteristics is going to shift, a PNP transistor in the emitter follower configuration, okay, this is the emitter point, okay, has been introduced. Okay, and together with that, these additional diodes have been introduced, so that they have direct connection, okay, to this point also. Okay. So that when any input goes low, this transistor here, okay, which is basically the phase splitter part, okay, that we have been talking of, this transistor can switch off faster. Okay. So that is the circuit modifications in the ALS series, okay, 74 ALS. All right. It is okay. And the other modification is higher resistances. So in the ALS series, okay, the properties, okay, the delay is 4 nanoseconds and the power dissipation is 1 milliwatt. So if you look at it, okay, if you look at the evolution of TTL gates, all right, starting from the standard TTL, where you had a power delay product of 100 picojoule, this has come down, this is the best, okay, or you can say the minimum power delay product of just 4 picojoules. Okay. So you have 4 nanoseconds delay, okay, and a power dissipation of just 1 milliwatt, okay, which is very good. All right. So from the circuit point of view, this is the last word in terms of TTL gates. Okay. So, but of course, if you want if you are interested in very high speed, you can go for AS series, advanced Schottky, which gives you the minimum delay. Okay. But if you are not so much concerned about speed, okay, you can of course go for ALS series, which gives you reasonable speed and very good power dissipation. Okay, I mean very good power dissipation in the sense very low power dissipation. Okay, all right. So this is how TTL series had gone from over the years. Okay, it has changed for about 2 decades. Okay, and after that, of course, not much has taken place. Okay, in fact, the trend has shifted now in the sense that later, okay, there were some 7-4 series compatible CMOS gates which have come up. Okay, they are basically CMOS gates, okay, but with the pin compatibility and total compatibility with 7-4 series. All right, that is basically you can replace a 7-4 series gate with a CMOS series gate. They are the 7-4 AC family, 7-4 AC or ACT. So, these are some of the families, they are basically CMOS families, all right, but they have pin compatibility with the 7/4 series as well as the input output compatibility, all right. And there of course the delays are about 5 nanoseconds or so, okay. But of course the advantage of CMOS is very low power, very low power dissipation, even much lower than this, okay. So that is another advancement which has taken place. Of course they are not the exact TTL family, but okay, now that is also available, all right, which is so a lot of further advancements have gone in that direction, okay. So TTL gate, just to summarize about TTL gates, TTL gates are basically what is available now are medium scale integration, okay, chips, okay, which where you get the different flip flops or even more complicated circuits like counters, shift registers, okay, and some other of these multiplexers, okay, and you can use them to make some small systems, okay, you can small or even slightly complicated systems, okay. So these are what are available, okay, and are being widely used even today, okay, to make systems, okay. And but the problem with TTL is that you cannot make very large scale integrated circuits out of TTL because of several factors. You see that it involves a number of transistors, okay, and the prevalence of a large number of resistors, okay, in this configuration. You see in integrated circuits it is very difficult, I should say that it is not advisable to have too many resistors because resistances take up a lot of area on the silicon wafer, okay. So it is so if you want to make a large scale integration, you must be able to avoid these passive components, resistors, capacitors as far as possible, okay. In fact the active components, okay, that is the transistors or the diodes take much less area compared to the passive components, okay. So for large scale integration this is not suited at all, okay. So we do not have very large scale, we do not have large scale integrated TTL circuits, but they are available in very large wide variety of circuits are available in, okay, as I said like gates, flip flops, okay, then counters, shift registers with which you can make a big system, okay, all right, and you can make your own circuit. If you have a circuit you can connect them together and make reasonably good circuits, okay, all right. So that is about TTL gates, okay. So we shall stop here about TTL gates and take up the next logic family, okay. The next bipolar logic family in our course, that is I squared L, that is integrated injection logic, okay. So and we shall again go through the same process, that is we shall see how it developed, okay, and what is its present status, okay. So I squared L or IIL, you know, sometimes stands for integrated injection logic, okay, all right. So well, to start with IIL, okay, we shall first take up a logic family, a very old logic family in which it has its roots, okay. So now we had again go back to our familiar transistor as an inverter circuit, the inverter circuit using a BJT, okay, all right. I should. So if you have this, so this is the circuit of an inverter using a BJT. All right. Now, suppose I connect another transistor here in parallel. Okay. What gate? So, if these are the two inputs and this is the output, say, okay, so A, B are the two inputs and Y is the output. Okay. What is the logic gate which you or logic function that this circuit performs? It is a no, it is a NOR gate. Okay. It is a NOR gate. Why? Because when any of this, see, if when any input goes high, okay, all right, basically this transistor conducts, okay, and this transistor is going to go to saturation, the output is going to go low. When both the inputs are low, okay, both are off, output is high, okay, and when one is high, one is low, of course, because one transistor is conducting, a current will flow, okay, and as the current flows there is drop across this resistance and the output is going to go low. Okay. So, basically when any input goes high, okay, the output is going to go low, which is a NOR gate. All right. So, this is a NOR gate. Now, suppose this output, okay, is connected. So, you have a 2 input NOR gate here, we have a 2 input NOR gate. All right. Now, this NOR gate output can be connected to some more NOR gates, say some more 2 input NOR gates. All right. Let us look at this circuit. Okay. This output of this NOR gate is connected to 2 further NOR gates. I mean, these are the 2 fan outs. Okay. So, you should be able to connect it. Now, suppose I connect it here. All right. There is another similar circuit here. All right. So, it comes here, say, and it's another 2 input NOR gate. And you have another 2 input NOR gate. Okay. So, this is this particular configuration. Okay. This one, the 3 2 input NOR gates, this 2 input NOR gate is driving these 2 input NOR gates. Okay. So, this particular logic family, which was early days, okay, it was called DCTL, okay, which stands for direct coupled transistor logic. This is because these transistors are directly coupled, okay, this output is directly coupled to the input of this transistor. Okay. All right. Now, this logic family had a it did not survive because of a particular drawback. Okay. The reason is, the drawback is like this, that the output is connected to the inputs of the different logic gates. Okay. And so, basically what you are doing is, you are shorting the bases of these transistors. All right. Now, these transistors, you know, they may be on different chips also. So, they may not be identical. Okay. This transistor and this transistor, they may not be absolutely identical. Okay. And the cut-in voltages of the base emitter junction, okay, or of these transistors may be slightly different. That is, the voltage at which this transistor starts to conduct, the base current starts to flow, may be different from this particular transistor. Okay. So, these transistors may be slightly dissimilar. Okay. So, what is going to happen? What is going to happen is that when this transistor starts to conduct, okay, say suppose the difference may be, you know, very very small, okay, maybe not 1 volt also, or maybe not 2 volts. Okay. But what is going to happen is, because of the exponential nature of the IV characteristics the input, okay, what is going to happen is, if this base starts conducting at a lower voltage, okay, this when this starts conducting, the voltage will become more or less clamped, okay, and this transistor is not going to get current, because the input voltage is not going to rise to the point when this is going to start conducting. Okay? You understand? So, because these are shorted, so when this starts conducting, the voltage here becomes clamped, all right, and this is not going to get the current. Okay? So, this particular problem has got a definite name, it is called the current hogging problem. So, that is basically one of the transistors is drawing most of the current, okay, and depriving the other, all right. Okay. So, this is the problem due to which, okay, this particular logic family is could not gain ground as such. Okay. Then now, if you look at this circuit again, all right, suppose I take this part of the circuit, this resistance up to here, okay, that is this part of the circuit, okay, that is this resistance here and these two transistors. Okay. I can draw it like this. You have two transistors, one more transistor like this, to going to VCC. All right, this part of the circuit. Okay. Now, just like we had multi-emitter transistors, okay, now if we can have a circuit which is something like this, you know, one base emitter junction and two collectors, and this one, instead of a resistance, okay, what we have is maybe a current source. Okay. So, this is going to be an equivalent circuit. Okay. That is basically what we are looking at is here the two base emitter junctions. Okay. That is, if you have a transistor with a common base emitter junction, okay, then of course there is no problem of you do not have the problem of current hogging, because there is the same base emitter junction, all right. And so, because these base emitters are in parallel, you see, these are emitters are grounded and the base points are shorted, okay, you can have a common base emitter junction, all right, and multiple collectors, okay, a transistor with common base emitter junction and separate collectors, okay, and instead of this resistance you have this current source, okay, all right. So, this is you can think of it this way. All right. Now, you can realize this current source. So, the next circuit which I will draw is I just replace this current source, I realize this current source using a PNP transistor. Okay. So, here it goes this way, all right. You have a resistance here, a VCC and a resistance here, okay. Now, this is the emitter, this is a PNP transistor, okay, emitter is this base of this PNP transistor is grounded, all right. Now, this emitter point is going to be more or less fixed, okay, at 0.7 volts, okay. So, the current, a constant current is going to flow, all right, VCC minus this emitter voltage by R, okay, and if this transistor has a high enough beta, okay, you can say that the collector current is almost equal to the emitter current, okay. So, this behaves as a current source, all right, okay. So, this we have replaced this current, I mean we have realized this current source using a PNP transistor. So, this configuration, okay, is derived from the DCTL family. Okay. So, this particular configuration which you have here is the basic I squared L cell, unit cell, okay, of the I squared L family, all right, a PNP transistor and an NPN transistor, all right. Now, the way it works is like this, again it is just similar to a DCTL, okay, that is you have a current source, okay. Now, if the input is low, what is going to happen? This transistor, basically you have here you have another of this connected cell connected here. So, you may have another of this connected here, output point. Okay. So, if this point is low, which means that this transistor, the next transistor is going to be off, okay, is not connected. And how is this low? Because this transistor is in saturation. So, this current source which is flowing here, the current which flows here is going to flow into the collector of this transistor, all right. If this transistor is off, okay, this output point is going to rise high, okay, and this current which is flowing here goes into the base of this transistor. So, basically the current source, the current from the current source either flows into the previous transistor if this is conducting, or it is going to flow into the base of this transistor, making this transistor go to saturation, all right. So, the voltage at this point is going to be either 0.2 volts if this transistor is in saturation, okay, or 0.7 volts, okay, if this transistor is conducting. So, basically the shift in the voltage here changes by a very small margin, okay, 0.2 to 0.7 volts, and the current either flows here or there. So, we shall see later how you can realize the different logic circuits using this, okay, all right. So, in fact, the I squared L logic family was invented, I should say, in the Philips laboratories at Eindhoven, Holland, okay, and, late 60s I think, or early 70s, okay, all right. So, okay, so you see that you have a structure here, okay, which is a very simple structure, one PNP, one NPN. This is the I squared L structure. Now, how do you realize it? Okay, we need to draw the cross section, okay, to see how this can be realized, all right. So, how do you realize it is you start with a wafer which is n plus on n, okay, then just you have a guard ring, okay, then this is the PNP transistor. I think I should. All right. So, this is P, this is N, this is P, N plus, okay. So, I think. So, this is these are the contacts, okay. Now, the PNP transistor which we have here, well, this is the PNP transistor, okay, and the NPN transistor, this is the NPN transistor, okay, all right. So, and this N, the contact, this is ground, okay. So, if you look at it, all right, this way, the PNP transistor, so this P region acts as the emitter of the PNP transistor, this N region is the base and this P region is the collector, all right. And this NPN transistor, the collector is here, base, and this is the emitter, all right. Okay. Now, so what this N region actually acts as the base of the PNP transistor as well as the emitter of the NPN transistor. So, you see that the base of the PNP transistor as well as the emitter of the NPN transistor is grounded. Okay. So, this is the ground region. Okay. So, this N region acts as both the base of the PNP as well as the emitter of the NPN transistor. This P region here acts as the collector of the PNP as well as the base of the NPN transistor. Collector of the PNP, so this is shorted here, collector of the PNP as well as the base of the NPN transistor. So, this is the collector of the NPN. Okay. So, these two transistors, okay, the PNP and the NPN are basically merged together, okay, in this particular configuration, and that is why this logic family is also called by the name of MTL, or which stands for merged transistor logic. Okay. MTL or merged transistor logic. So, in initial days it was also called by that name. All right. So, so this is the particular configuration of the I squared L structure, this structure. The advantage one you can see is that because of this merged transistors, okay, the area required is very small because you are merging the two transistors, and in fact the I squared L transistor family does not require any resistances. Okay. In fact, this resistance which you see is usually is external to any chip which you fabricate. Okay. It is this point which is available, all right, and this you can connect the supply voltage through a resistance. Okay. And so, this I squared L family is ideally suited for large scale integration, that is very complicated logic circuits. Even microprocessors have been made using I squared L. Okay. So, this is the only bipolar logic family, okay, which is suited for very large scale integration. All right. So, that is the strong point of I squared L. Okay. So, yes, in fact, I think there will be a lot of questions in your mind about this particular structure. Okay. Why we start with n on n plus, and so see the point here is because of this particular structure, the transistor, the NPN transistor is actually inverted. Okay. That is, normally you have the emitter on top and collector on the bottom. Okay. But in this particular configuration, just to enable us to have a merged transistor structure, okay, the collector is on top. This is the collector. Okay. So, if this is the collector is on top and the emitter is on bottom. Okay. I will also draw the top view of this cell because we shall be doing a lot of this in. Okay. So, this is the n plus, which is the guard ring sort of. I shall also explain later why we require a guard ring. So, you have these contacts, sorry, you have these are the collectors regions. Okay. Okay. So, this is the injector contact. This contact is called the injector contact. Okay. That is basically the emitter of the PNP transistor, that is called the injector contact. Then you have the base contact. Then you have the two collector contacts. I will call them C1 and C2. All right. C1 and C2, the two collector contacts. These are the collector diffusions done inside the base region. Okay. This is the base contact, and this is the injector contact. So, this is just gives you the top view, and this is the cross section view. In the next class, we shall take up more detail and discuss why we require this particular structure. Okay. And then we shall go ahead and also see how you can realize other logic gates like NOR or NAND, okay, using the I squared L structure and even more complicated circuits.